Now in our last part of Lesson 7, we're going to do a few practice problems to reinforce what we learned last time, which was we learned about energy diagrams or enthalpy diagrams. And so in this lesson, we're going to practice that skill a lot more. We're going to introduce one new way to actually represent how much heat is being absorbed or released, and that is to write what I'm going to call thermochemical equations. Now, it's a really fancy word, and it's not one that you actually need to know. I'm never going to expect you to write this, but you can see what it is. You know, we've had chemical equations before, but a thermochemical equation includes the heat value in the balanced equation. Now, we're not really going to be balancing equations, but you'll see what I mean in just a second. All right, let's look at this reaction. So this reaction you may have done in class before. Some years I do it in my class, but I fill a balloon with hydrogen. That's what's in this balloon right here. And I usually bring a flame near it, and it explodes violently by reacting with oxygen. And you get this huge fireball that's going on there. Now, I want you to think about what we know about that reaction. Is that reaction more likely endothermic or exothermic, based on what you're seeing? And which of our diagrams, our enthalpy diagrams, would be more a stronger representation of what's going on here? Well, being that it's releasing so much heat is coming out into the world, the chemicals must be releasing heat. I think it's definitely an exothermic reaction. We are predicting that this is what its diagram would look like. In other words, the reactants are giving away heat, and since the heat is going out, that means the products have to have less potential energy in them. And you can see that in the delta H, right? The enthalpy, remember we call that enthalpy, is negative 106, right? It's giving away heat. Anytime the sign is negative, it means that heat is leaving that system. So we know the sign of delta H should be negative. We're measuring it in kilojoules, and the amount of heat lost from there to there is negative 106 kilojoules. So we learned about these enthalpy diagrams, but what are we talking about here when we're introducing this idea of thermochemical equations? Well, very often we will give you the amount of heat gained or lost in a number form like this. And it's pretty easy when it's given this way, because if you come right in here and you say, okay, I have this negative sign, I know heat's going to be given off or lost, I know that it's exothermic. I know that it's losing energy and the product should be lower in energy than the reactants. But in a thermochemical equation, there's another way to represent the energy, which is to put the energy in the balanced equation, just as if it's a reactant or product. So here I might look at this equation and I might say, look, it's giving away energy. It's releasing that energy. And I might view that energy as a product. So I'm going to actually include the energy in a reaction. Now, if you're sitting here thinking, well, how do I know whether to put the 106 kilojoules of energy on the reactant side or the product side? And also, why did he just get rid of that negative sign? Well, that's what we're going to talk about today, is how do you know those things? But that's what a thermochemical equation is it includes the energy in the diagram. So I'm going to give you a rule about which side to include the energy on, but then we're going to try to see if we can make it a little bit more concrete for you. Well, the first thing is I got rid of the negative sign because this sign right here does not mean that I just made it positive. Remember that the plus sign in reactions means and. It means the word and. In other words, hydrogen and oxygen were reacted together. It's not a mathematical plus or minus. So hydrogen and oxygen were reacted together to make some water and 106 kilojoules of energy. The energy is over here because it was released. It was made in the reaction. It wasn't consumed in the reaction. It wasn't used up. Whereas if we were to look at another reaction, if you look at this reaction, which, you know, this is mercury oxide. I've never actually done this reaction before. But if I look at its delta H, it's positive 290 kilojoules. That means energy is going to be entering the reaction. We know that it's endothermic. Because that energy is going to be entering the reaction, that means it's going to be absorbing that energy, so the products will be higher in energy than the reactants because they'll be taking that energy in. Makes sense. So we're going to be gaining 290 kilojoules of energy from the reactants to the products. Well, if we want to decide which side in our thermochemical equation to put the 290 kilojoules, remember rule number 1 is even if there was a sign on it, we're not going to include the sign, and then we just got to decide which side it goes on. Well, if it's absorbing that energy, it's entering the system, it's a reactant. The energy is sort of coming into the system, so we're going to put it on the reactant side. No sign whatsoever. Just put it in there as if it's another reactant. So now we're saying that mercury oxide absorbs 290 kilojoules of energy to make these two chemicals. Now, there is a rule to this, and you could write it down. It's a good idea to write it down. So which side do I put the energy on? Well, in exothermic reactions, the energy value is written on the product side, like the example up here. In endothermic reactions, energy value is written on the reactant side. And I might also put in there, you might want to write in there that don't include signs, right? No positives and negatives. It's the side that you put it on that tells me whether it's really positive or negative. Now, these rules, fantastic, but I'm not a person who really believes in memorization, so I'm going to give you, of course, a little bit of a metaphor to help you think this through, because you got to know which side they go on. So these are the same two reactions, nothing's changed, and I've added this rule, never use the negative sign in your reaction. But here's my metaphor. Okay, so here are my two scenarios, and let me tell you what the Y and the M stand for, and we'll see if you can decide which scenario you prefer. So the Y in this stands for you, as in you, the person, individually you, and M stands for money. So what I want you to do is I want you to look through these two scenarios and see which one of these two scenarios you would like better. Well, if it were me, I would like a scenario number 1 a lot better. Because actually scenario number one is you gaining money, right? Let's see how it works. In the beginning, here's you, and you notice you don't have any money on you, it's just you. And in the end, you and money are together. That's why you're written together over here. So you without money and money without you and money come together to make you with money. This is you gaining money. And of course, in this little metaphor, I mean the money to be the energy, right? This is endothermic to you. You're gaining something. Whereas look over here. Over here, you have the money. You are together with your money. It's in your pocket. That's why you're written together. And then later on in the product side, there's you without your money. Your money has been separated from you. So you with money becomes you without money, and money goes off on its own. That means it's releasing money. And of course, in this case, money is a metaphor for energy. So the chemicals have the energy in the beginning, but then the chemicals don't have them and the energy is released. So that's why whenever you're releasing energy, it's written on the product side. And whenever you're absorbing energy, it's written on the reactant side. It's a pretty cool metaphor. You might want to see if you can come up with another one. But let's see, over here we said this is releasing energy. If it's giving away energy, it went on which side? It goes on the product side because it's giving away that energy just like you were giving away energy here. 106 kilojoules. Where over here it's absorbing energy. The sign tells me that. It's endothermic. Since it's absorbing it, that means it's got to be on this side. So this chemical absorbed 290 kilojoules of energy to make those. So you could either memorize this little, idea that I have here, but I wouldn't memorize it. I want you to think about some scenario that makes sense to you. And if you like my metaphor, you definitely can use that. Okay, so let's do a practice problem together. So what I want you to do here is I want you to pause the video and I want you to answer these questions in your Google Slides.